Hello everyone, my name is Gregory and welcome back to ChemCore. In this video, we're going to be discussing the worksheet for leveling effect and reaction completion. And if you haven't watched the topic instructional video on the leveling effect and reaction completion, I really suggest you go watch it. It's only a couple minutes, it really clarifies some things, and it's in the description below. And if you haven't had a chance to look at this worksheet and the answer key, that is also in the description below. So make sure to go check that out before I walk through it. Now, if you haven't been, to any of my explainer videos, this is just me step by step going through each problem, solving it, and kind of thinking it out loud, right? Explaining every part of the question and going through it as I would by myself. And so I won't remind you guys what the leveling effect and how reactions go to completion. This worksheet is kind of going to summarize the entire unit, not only these two topics. I'm really going to kind of put together all of the acid and base principles that we've learned this unit, including your laws like Bronsted-Lowry and Lewis acids and bases, as well as the general definitions and how they work, as well as mechanisms and your principles of acid and base strength. The rules of REO. And if you don't know those, or if you're unfamiliar with some of them or not super confident, everything is absolutely for free, available in the description below or on my website, linked in the description. Now let's start. Which of the following best describes the leveling effect? Let's go through each answer choice and think about which one is probably incorrect or correct and for what reasons. So A says that the ability of a compound to dissolve in a given amount of solvent. Remember that the leveling effect really talks about which solvents that we can use regarding to the strength of an acid and the strength of a base. Remember that certain acids and bases, although they're strong, technically because of the solvent, their acidity or their strength of their acidity and basicity could be changed. It also kind of causes what kind of solvent can we use, because we don't want the solvent to interact with the acid and base. We want the acid to protonate the base, and vice versa. We want the base to kind of take the proton away from the acid. We don't want the solvent to be there because of it. And so this kind of doesn't make sense. It really doesn't refer to any of the principles that we talked about with the leveling effect. Now, B really is kind of the definition of the leveling effect, the textbook definition that I described in the video, the limiting of a compound's acidity or basicity by respective deprotonation or protonation by the solvent. Now, for example, if I were to give you an acid, like a strong acid, like H2SO4 with some generic base, and you would say, okay, 100% of the protons would go onto this base. The problem is what if the solvent were to get protonated instead? That would kind of limit how much of the protons can actually go on the base. Not 100% would do that, because instead some of the some of the solvent gets protonated. And so this is probably the closest answer choice to defining the leveling effect. C says the cause of weak acids or weak bases to incompletely dissociate in water. Now, is this answer choice kind of like in theory untrue? No, the weak acids and weak bases don't completely dissociate in water. That's true. The problem is that has nothing to do with the leveling effect, right? It doesn't describe anything that regarding the leveling effect about solvents and stuff. Weak acids and weak bases don't completely dissociate in water because of their own properties, right? They're not able to kind of gain the amount of electrons that are needed to let go of the proton, and some of the principles that we talked about in the REO video. Answer choice D says the reason that explains why moving down the periodic table results in compounds that are more acidic. Not really. We kind of discussed that in REO, why this happens, and that's more because of the fact that maybe the atoms are bigger, and so they're able to kind of get more electrons, and opening a new shell isn't that much of a big deal. There's other principles about it as well and other reasons, but nothing to do with the leveling effect. And E says the reduction of inductive effects as electronegative atoms are moved further from the acidic proton. This is also regarding to REO, in specific I in REO, the inductive effect. Now remember that the inductive effect is a property in which electronegative atoms can help pull some of the negativity away from the acidic atom, increasing its acidity, right? And the reason why, okay, if we move this electronegative atom further away from the acidic atom, well, then the effect of it becomes less because it's further away. It's kind of like reaching and grabbing for some of the electrons, but it's hard to reach. And so because of that, really nothing to do with the leveling effect. And so the answer choice that best fits our definition of the leveling effect is B. In question 2, we're asked which of the following solvents can be used with NaNH2. Now, some of these questions might be a little confusing. What do you mean, what solvent? Well, the reason is okay, regardless of what acid we use, understanding that NaNH2, because of that extra lone pair on nitrogen, is a base. Now, regardless of what acid we can possibly use with NaNH2, which solvent of the choices would least likely kind of affect the reaction, would kind of least likely change what's going on or change the product's form? And if we just use liquid NH3, think about it. If we were to protonate NaNH2, this would form NH3, right? And so if we use NH3 as a solvent, this would least likely change the reaction. It wouldn't change the reaction at all because we're still forming NH3, right? There's no extra compounds being formed. There's nothing extra being protonated or deprotonated. And so because of that, that's the best solvent we can use. In question 3, we're asked which of the following solvents cannot be used with CH3,3COK. This is like a really big complicated molecule. Doesn't matter. We have to think about it. If we're assuming that this acts as the base because it has a negative charge, right? Obviously, it's going to act as the base. Which of the following solvents would least likely kind of interfere with the whatever acid we can put in this equation or this reaction? Which solvent would least likely kind of interfere with the protonation of this base? Now, think about it. A, we don't have a very acidic proton there, right? The only protons that may be donated are on the carbons. That's probably not going to be donated, right? And so that's not going to interfere at all, right? It's definitely 100% we could use this acid or this we could use this solvent. B, CH3,3COH. Now realize that this is just the conjugate acid of our base, right? If we were to protonate this, right, get some H, this would go right to the O and we would form this product, right? B. And so if we use this as a solvent, what are we interfering with? We're forming the same exact thing. The same things are getting protonated. And so B is absolutely a solvent we can use. Now, in answer choice C, we're given H2O. The problem with H2O is that H2O can act as both an acid and a base. The fact that both of the protons, H's, are attached to the O in H2O, this brings up a problem regarding the environment that it's in. It is possible, 100%, with the base that we're given, that H2O, if combined with a strong acid, if it was a strong acid, who's saying that H2O can get protonated instead, right? Instead of the base that we want. It's possible. And also, H2O instead could be the one donating the proton. And so in both ways, kind of, regarding depending on what kind of acid is in the environment, it is possible that H2O as a solvent is actually going to, show us an example of that leveling effect. It's going to interfere with that base, right? It's going to interfere with that reaction happening with that base. And so probably H2O is not a solvent that we can use. Now, liquid NH3, though, you might be confused. Okay, why can't NH3 do this? NH3 is not very strong. It's not strong enough of an acid, right? If we had to compare H2O and NH3, NH3 is not strong of an acid to donate to oxygen, right? Oxygen is a stronger acid, meaning it's a weaker base, right? And so if we're considering which one wants that hydrogen more, it's nitrogen. Nitrogen wants that hydrogen more. Why would it donate it, right? And so NH3 is probably not going to be interfering with the reaction. Now, THF, I'm not going to draw out the structure. I'm going to put it on the screen. Now, if you look at the structure, you'll be able to see that THF can easily interfere with the reaction. And so because of that, it's 100% possible that THF could interfere with the reaction of the base. It could be the one to donate. And so because of that, the solvent that'll probably not be able to be used is water. Now, water is kind of the universal solvent. You might remember that from your previous chemistry courses or this course. Not always, though, right? Especially with acids and bases and some of the reactions that we learn in the future, water is not really a great solvent, and it could instead actually cause some problems with your reaction. And sometimes if you use water thinking it's a universal solvent, you'll actually mess up the reaction and get the whole reaction wrong. And so starting now, you really have to be careful with what solvent you have to use. In question 4, which of the following solvents can be used with CH3,3CLI? Now, obviously, since this is negatively charged, this is going to act as our base. And so assuming that we're going to have some acid in the reaction mixture, we have to choose a solvent that is not going to interfere with the transfer of protons from the acid to the base. Now, answer choice A, we have this acidic proton attached to an oxygen. The problem is that oxygen could very well donate the proton to carbon, right? That instead is going to interfere with the fact that the acid donates to the base. it might instead be the solvent. And so this is probably not the great solvent to use. The same reason is with B and C. Now, if you notice with B and C, with the alcohol, or don't know what alcohol. In B, the alcohol, the hydrogen is also attached to the oxygen, and so as well in water, right? The hydrogen is also attached to water. The hydrogen is also attached to oxygen, meaning that it's very possible that the oxygen could instead donate the proton instead of the acid that's in the reaction mixture, and that's going to interfere. Now, similarly, even though in D, the hydrogen is attached to nitrogen, it's still much stronger of an acid than the conjugate acid of this guy is, right? Because of that, this liquid NH3 can 100% donate the nitrogen to the base, and it'll interfere with the reaction. Now, E, even though it's not the exact conjugate acid of the base, the fact that all of the hydrogens are attached to carbon and they're all sp3 hybridized, just like the bases, means that there's not really a significant difference in the acidity or basicity of these two compounds. And so because of that, it's very, very, very unlikely that answer choice E is going to donate to the base and interfere with the reaction. And so this is probably a really great solvent to use. Now, question 5 says, as a result of the leveling effect, the strongest acid that can exist in appreciable concentration in aqueous solutions is. Now, this is exactly the issue that the leveling effect brings up with acids and bases. The leveling effect states that the actual solvent, or the acidity of a strong acid and basicity of a strong base, is actually limited by its environment. H2SO4, in theory, wants to donate all of its protons, right? Wants to donate all of those H's. Not all of those H's, but the first H, the H2. So same thing with HCl and HNO3. They're all strong acids. The problem is that water, H2O, can also accept that proton and become H3O+. And so because of that, the strong acids in a solution aren't going to, if we examine an acid-base reaction with a strong acid, the theoretical ability of the acid to donate the H+ is actually limited by water, right? Because water ends up taking that H+ and becoming H3O+. And now H3O+, hydronium, is the one donating the proton. And so because of that, H3O+ is limited by strong acids are limited by H3O+, meaning that the strong acid that can exist is H3O, right? Hydronium. And similarly, in question 6, the strongest base that can exist in an aqueous solution is now the opposite, right? The H2O, when it's deprotonated, becomes OH. And so OH, even though there's a lot of strong bases, theoretically the strong bases are going to act, but in reality, because of H2O's limiting ability and it gets deprotonated, HO- or hydroxide is actually the strongest base that can exist, because of the fact that if we were to abstract the proton, we're abstracting the protons to become HO-. Question 7 says, why is ethanol a better solvating solvent than tert-butyl alcohol? Now, there are some properties, even though they're both alcohols, right? Ethanol and tert-butyl alcohol, even though they're both alcohols, meaning that we both have H attached to the oxygen, there's some properties that might be different between ethanol and tert-butyl. Now, what I want you to do is let's draw this out, right? Ethanol looks something like this, and tert-butyl looks something like this, right? And so because of that, maybe the structure of ethanol and tert-butyl alcohol can help us actually differentiate why the properties of the two might be different. Now, A says that ethanol is less sterically hindered and more capable of interacting with a solute. Now, absolutely, right? This OH, right, the acidic oxygen, is much freer, right? There's more space around the OH compared to the tert-butyl. It's like packed up, right? All of these other carbons are kind of blocking the interactions that OH can have. And that is probably part of the reason why ethanol has the different properties. Tert-butyl alcohol is less sterically hindered and more capable of interacting with a solute. That's like absolutely the opposite, right? Tert-butyl has a lot of these carbons kind of blocking it, causing more steric hindrance and less capability of interacting with stuff, meaning the solute. And so this is untrue. Ethanol is less sterically hindered and less capable of interacting with a solute. That's kind of like, half and half correct. It is less sterically hindered. Because it's less sterically hindered, it's able to interact more. There's more space around this acidic oxygen to interact with other things. And so because of that, that second part of the answer choice is not true. D says tert-butyl alcohol is less sterically hindered and less capable of interacting with a solute. Although it is less capable of interacting with a solute, that's because it's more sterically hindered, right? There's more stuff around it, and it's not able to reach the solute as well. And the last answer choice, terbutyl alcohol has more carbons than ethanol, making it more soluble in aqueous solutions. It does have more carbons, right? 3 more carbons or 2 more carbons than ethanol, but does it make it more soluble in aqueous solutions? Remember your properties of hydrocarbons. The more carbons that we have, the less soluble it is in aqueous solutions, right? Aqueous means water. Kind of carbons, as we add carbons, they become less miscible in water and more miscible in oils or other nonpolar compounds. And so because of that, although it does have more carbons, that part's true, the second part is untrue. And so our best answer choice is A. Question 8 says the compound aniline C6H5NH2 has weakly basic properties in aqueous solution. In this other solvent, aniline would behave as a strong base. And so which solvent of the list would cause aniline to kind of have the most basic properties? In other words, which one would least likely interfere with the acid donating protons to aniline? We want all of the acid to kind of donate 100% as much as possible to aniline, making it a strong base. And so because of this, A will 100%, this oxygen, since the acidic proton is attached to oxygen, can 100% donate to aniline. That's going to cause the acid, whatever acid is in the reaction mixture, to kind of be limited in its capability of donating that proton, meaning that not a good solvent for it to act as a strong base. It's the same reason for B and C, right? Both of these acidic protons are on oxygens. Even in C, it's actually a carboxylic acid, and it has a bunch of these electronegative groups, meaning that we have some inductive effect. This is the strongest acid of the list, meaning that both of them, B and C, for the same reasons as A, and C especially, are going to interfere with the acid's ability to donate to aniline, meaning that it won't act as much of a strong base. Now NH3, even though NH3 is close to aniline, the fact that hydrogen is still attached to nitrogen allows for the small possibility that nitrogen instead can donate to aniline, causing it to not be as much of a strong base. Now E, all of the protons are attached to carbon, meaning that it definitely won't be able to donate. It won't want to donate at all. All of them are sp3 hybridized. Those are the least acidic compounds that we can possibly have, meaning that in the solvent, assuming that we have an acid in the reaction mixture as well, aniline would definitely act as a strong base because all the protons from the acid are absolutely going to be absorbed or taken up by aniline, and not the solvent is going to have nothing to do with the reaction. In the next question, we're trying to figure out which one of these answer choices can act as a protic solvent. Now, it's important to realize that any of these compounds, as a liquid, can act as a solvent, right? But which one can be protic? And so it's important, before solving this question, to realize what protic means. Protic means able to participate or donate hydrogen bonds. This means that we must have hydrogen bonded to either oxygen, nitrogen, or fluorine. And so that's an important concept because only one of our answer choices, B, has hydrogen attached to either a nitrogen, oxygen, or fluorine. Remember, we talked about this earlier in Unit 1, I believe, when we talked about intermolecular forces, when we talked about hydrogen bonding. H bonds are just FON or NOF. And so nitrogen, oxygen, fluorine, or the other way around, doesn't really matter. In question 10, we're asked which one of these bases is the strongest one which can be used and retains its basic character in aqueous solution. And so what you want to realize is that even though we could have strong bases and strong acids, if we have a solution, some of the water molecules in the solution will be deprotonated to form OH, which can act as a base. And so the bases of the solution, the whatever reaction we have, are limited in their strength by water, because the OH is actually what's becoming the base. And so the strongest base that can actually exist in solution is the OH. In question 10, we're trying to figure out the expected product for the following reaction. And so in some of these problems, and this problem and kind of the rest of the problems, we're going to combine all the concepts that we've talked about in this unit, including acid-base strength, Bronsted-Lowry definitions, Lewis definitions, as well as the idea of being able to draw out a reaction. And so one of these concepts that we have to talk about is, well, can we draw the major product of an acid-base reaction? And so what you notice first is that neither of these reactants have hydrogens. And so we can kind of automatically eliminate the idea that this might be a Bronsted-Lowry acid-base reaction. It's definitely not, because there are no hydrogens to donate or accept. What we can kind of determine is that this must be a Lewis acid-base reaction. And what we can also notice is that sulfur, because it's sulfur, will have 2 lone pairs. And boron, because it likes to form 3 bonds and no lone pairs, is going to have no lone pairs. And so what we can also assume is that, okay, if an acid-base reaction has to happen, we have to have something that donates the lone pair, or the base, and we have to have something that accepts the lone pair, or the acid. And so if we have a base, if you're not familiar with these concepts, I really suggest to go back and check out that video where we really deeply discussed Lewis acids and bases. What you realize is that, okay, if we only have a lone pair in one of the reactants, then only that reactant can be the base, and it's kind of no question from there. And so remember how we draw a mechanism. We're going to take this lone pair, and this lone pair is going to attack the boron, and we're going to form something like this, right? I always like to kind of draw the product and then match it to one of the answer choices. And so it's going to be something like this. I'm not going to write BF3. I'm just going to write B. But what we also have to realize is that on the left side, our net charge was 0, right? We didn't have a charge on any of the reactants, which means in the product, in this one product, our net charge, or overall charge, must also be 0. What you'll also realize, okay, boron now has an extra bond, which means we have a -1 formal charge. But there has to be something that equals out that negative formal charge to get a net charge of 0, which means sulfur now must have a positive form charge, which makes sense because it lost that lone pair. And so the answer choice that best matches that is the fourth structure, which is answer choice D. Question 13, we're working through a similar problem, in which case we look at both of the reactants. Again, we don't have a hydrogen to donate, and so we can't have a Bronsted-Lowry acid-base reaction. This must be a Lewis acid-base reaction. And so what I like to do first is, okay, let's locate where the lone pairs are. Oxygen always likes 2 bonds and 2 lone pairs, and aluminum, which looks a lot like boron, will have 3 bonds and no lone pairs. And so remembering your Lewis acid-base definition, your base must have a lone pair, right? Because it's the donor of the lone pair. And the acid might not have the lone pair because it's going to be the one that accepts it. And so what we can say is that this must be the base because it's the only reactant that has a donatable lone pair. And the aluminum trichloride must be the acid. And remember your mechanisms, the lone pair will reach out and attack that aluminum. And what we end up forming is we still have that ring like this. We still have that double bond oxygen. And we're going to be connected to the aluminum and then Cl3. And what you now realize is that aluminum now has an extra bond, which means we have a negative formal charge. But oxygen now has 3 bonds and just 1 remaining lone pair. We lost a lone pair, meaning that we have a positive formal charge. And the answer choice that best matches that is structure 2, or answer choice B. In question 14, we want to identify which one of these is the acid, which one of these is the base, and then finally, which one is our product. Kind of nothing different than what we did in the previous problem, except now we're also asked about our acid and base, which to begin with, we located our acid and base to begin with. It doesn't really matter. Nothing much more. What we want to realize first is that the only structure that I have a donatable lone pair is on this carbon. Remember that carbon, a negatively charged carbon, will have 3 bonds and a lone pair. While on this nitrogen, we don't have any lone pairs, right? We have 4 bonds, an extra bond than what we like. And so we know that if we have a Lewis base, the only Lewis base that can be possible is this carbon, right? We can only have one of these Lewis bases. And now, if we want to consider which one is the acid, our acid must be over here, right? Because we don't have any lone pairs. But what you'll also notice, unlike the previous 2 questions, is that the acid now has donatable protons, right? And it definitely does want to get rid of the protons. Remember, in the REO video, positively charged nitrogens are actually fairly strong, even stronger than alcohols. And so one of these hydrogens can definitely be donated. And so remember that what happens is that our lone pair will reach out and grab one of these protons, and this bond will break, and the 2 electrons in the bond will go over into nitrogen. And so both our products, what our products are, is we'll have this benzene ring. I know they kind of drew it sideways, but I'm not comfortable drawing it like that. So I'll just draw it like this. We have just regular nitrogen with 2 hydrogens now in that lone pair. And now we have HCN because it just grabbed that hydrogen. And so the answer choice that kind of best matches that. Oh, one more thing is that we can't forget our spectator ions. We had sodium and chlorine. And so one of our side products that we usually don't draw, but in this case they kind of want to see it, is NaCl, right? They didn't disappear anywhere. They're just kind of hanging out next to each other now. And so what we want to say is that structure 1 was our acid, structure 2 was our base, and then the products were structure 3, structure 5, and structure 6. And so the answer choice that best matches that up is A. Now in question 15, we want to identify the acid, the base, and then predict the position of the equilibrium. And so now we're really testing on the ideas of reaction completion. Remember that even though sometimes we are able to like kind of draw an acid-base mechanism, doesn't mean it's always like going to happen to an appreciable amount. It's not always going to be a successful reaction. Remember, the rules is that we want our acid to be stronger than our conjugate acid and our base to be stronger than our conjugate base. But to decide that, we really should draw out our conjugate acid and draw out our conjugate base, because otherwise we wouldn't really be able to decide that. And so what we want to notice is that, okay, right here, this reactant has a donatable proton, right? And we definitely know that it really wants to donate it based on our Oreo video. Positively charged oxygens are pretty damn acidic, right? And so what we also notice is that this negative charge is on the carbon, which means that this carbon has a lone pair and 3 bonds. And so what can definitely happen is that this lone pair can reach out and grab one of these protons, and then this bond will break and the protons will go over to the oxygen, meaning that our final products should be something like this. And everything is kind of, we don't really have any charges anywhere else. Remember that on the left side, our net charge was 0, and on the right side, our net charge was 0. Let's also label that this was our base, and this was our acid. And now let's determine, based on those rules, how can we determine where the reaction will favor, whether it'll favor the left side or the right side. We can also kind of determine, okay, if we look from right to left, what we'll notice is that this structure now accepts a proton, meaning that this must be the conjugate base. And now this structure, since it kind of donates a proton, must be the conjugate acid. And now what I want you to do is compare the acid on the left side to the conjugate acid on the right side, and the base on the left side to the conjugate base on the left side, on the right side. And so what you'll notice is that this acid, this proton, remember your Oreo rules, this proton is connected to an oxygen, which also is positively charged, while this proton, which ends up getting donated, is connected to just a regular sp3 hybridized carbon, meaning that this acid is a lot stronger. And now if we want to compare the base on the left has a negative charge, while the base on the right has no charge, right? It doesn't want a proton. The base on the left definitely wants a proton. And so this base is much stronger. And so what we can assume is that structure 1 is going to be the base, structure 2 is going to be the acid, and it's going to favor the right side, meaning that the best choice that matches this is B. In question 16, we have a similar problem in which we're identifying which one of the reactants is the base, which one of the reactants is the acid. And if you haven't watched the previous question, I'll just go through it the same exact way. We also want to predict the position of the equilibrium. Now, what you'll notice is that, okay, to predict the position of the equilibrium, the rule is that the acid must be stronger than the conjugate acid, and the base must be stronger than the conjugate base in order to favor the right side. If that doesn't happen, it's just going to favor the left side. It's just going to go right back into the reactants. To do that, a good idea is probably let's draw out the conjugate acid and the conjugate base. To do that, we kind of have to draw a mechanism and figure out what's going on. And so what I notice is that on this right side, we have this positively charged nitrogen with donatable protons, meaning that hell yeah, it can definitely act as an acid. It's actually pretty strong. Remember, stronger than even alcohols. And on this left side, we have this oxygen that has a negative charge, meaning that it has an extra lone pair. And it's totally possible that one of these lone pairs can reach out and grab one of these protons, and the bond that this proton is held by can break, and these lone pairs can just hop onto the nitrogen. And then our structure, our products, sorry, I'm drawing over the question mark, is going to look like so. What you'll also notice is on the left side, we have a net charge of +1, and on the right side, we have a net charge of +1. Let's also write down that this was our acid, and this was our base. And so what we realize, if we're looking backwards, this guy absorbs another proton, meaning that this must be the conjugate base. And this product donates the proton, meaning that this must be the conjugate acid. Now we should compare the acid to the conjugate acid and the base to the conjugate base. And so what we'll notice is that, okay, this acid has a positively charged nitrogen, but that's the acidic atom. But the right side, the conjugate acid, the acidic proton is connected to an oxygen. Now, be careful. This is where your ARIA rules become really handy. This oxygen is a carboxylic acid. Remember your exception rules. A positively charged nitrogen is stronger than an alcohol, but weaker than a carboxylic acid, which means that actually the conjugate acid is stronger. What you can also notice is that this is the base, and this is the conjugate base. Remember, the way I kind of taught you guys to remember which one could be a stronger or weaker base is just to imagine it's as acid form and then determine which one is the stronger acid. And so if we kind of have to determine its acid form, if we put an H in front of here, we would imagine this oxygen as being much stronger than an NH2, right? Even it's also a carboxylic acid. And so because of that, if this acts as a stronger acid, this guy must be the stronger base, right? Stronger acid, weaker base. Weaker acid, stronger base. And so because of that, since the right side, the products are stronger than the reactants on the left side, the reaction will generally move to the left. And so what we can say is that answer choice D matches our prediction, right? Structure 1 is the base, structure 2 is the acid, and it's going to favor the left side. In question 17, we're being asked when proton transfer reactions reach equilibrium, there have been formed the weaker acid and the weaker base. Probably when reactions kind of happen and they eventually are allowed to reach equilibrium, we want to go toward the products that are weaker as an acid and weaker as a base. In general, that's where the reaction is going to go toward. And so this is probably our answer. And it is, right? We don't want to favor stronger acids or stronger bases. That's just how the reactions happen. We want to favor weaker stuff. Question 18, we're being asked, acetic acid dissociates more completely. And now I know that you probably don't know what acetic acid is. It's kind of a common name for something like this. It's a carboxylic acid. And so if you're able to search that up and figure out what acetic acid is, that's all right with me. Now, what dissociates most completely and what are we being asked? Well, remember that dissociation is kind of a fancy word for donating protons. And so what they're really asking us is in which of the reactants, if combined with acetic acid, would be able to allow acetic acid to donate the most protons. And so we want to look for the thing that can act as kind of the best base, right? Which one can accept the protons the best? Now, if we looked at CCl4, you'll definitely kind of be able to eliminate it and say, hey, this definitely can't accept any protons. Carbon already has 4 bonds, and it's definitely not breaking any bonds with chlorine. And so how can it accept any other protons? Definitely won't happen, right? Same thing happens with answer choice B, except now we have 2 carbons. Doesn't matter, all of them have 4 bonds, and all of them have pretty strong. Each of these bonds is not something that we can just break, right? It's not going to happen. We can't just break one of these bonds and accept another proton. And so we can eliminate answer choice B. Now, H2O, we definitely know that it could act as a base, right? Is it going to be the best base? No, right? But it definitely could happen, right? And so it could allow acetic acid to dissociate to a pretty appreciable amount since acetic acid is much stronger than water as an acid. And so this is maybe, right? This is going to be our maybe. Now, the next problem, something like this. Remember that we have 2 carbons on each side. It looks a lot like water, and so you're kind of comparing, okay, which one, water or this ether, is going to act more as a base, right? Which one can act more as a base? Remember that as the carbons go up, acidity decreases because this is kind of the opposite of inductive effect, right? Inductive effect, we're putting electronegative groups around the acidic atom to increase acidity. Carbons are not electronegative. They're considered electron donating. Adding more carbons means that the oxygen is going to be less willing to hold an extra proton. Meaning that, okay, can it accept another proton? I mean, sure, but I think the water is going to be much more willing to accept another proton from acetic acid, allowing it to dissociate more completely. Question 19, the amide ion NH2- is a base which can be used only in which of the following solvents shown below. Remember, this is similar to a question we did earlier in the sheet. If amide ion acts as the base, which it probably will if you had to guess because it has 2 lone pairs and a negative charge. If it acts as the base, meaning that it gets another proton, it's going to become just ammonia, right? NH3. Meaning that clearly the best solvent we can use with this is liquid NH3 Because liquid NH3, the solvent, is not going to act as a better base than the amide ion. It's not going to accept protons instead of amide, right? So, and the product, NH3, is the same as the solvent, so it's not interfering in the reaction with amide ion and whatever acid we can possibly have, along with it. And so the best solvent to use, and the only solvent you can use, is E, right? Liquid ammonia. This question concludes the worksheet on the leveling effect and reaction completion. It also concludes all of the videos of Unit 3. And so if you're not familiar with the concepts we've been discussing in Unit 3, I really suggest to go back and watch either those topic videos or the explainer videos. It's always for free. You're always accessible. And if you're feeling like retrying this worksheet, it's always available in the description below. And the answer key is always available in the description below for absolutely free. So I'll see you guys in the next video.